Alright, welcome back to our latest topic. I think this is going to be conservation of momentum. This is Unit 6.2. So in Unit 6.1 we looked at what is momentum, and momentum is nothing but mass times velocity. A lot of very basic problems will just have an object like a baseball thrown. It might have a mass, let's say 0.25 kilograms, of velocity of 10 meters per second, and they'll just want to know its momentum, which would end up being 2.5 kilogram meters per second, and it would be a positive since it's moving towards the right on the screen as we've got written here. But anyway, do pay attention to these problems for things going left and right and up and down. That's in all your momentum problems. I want to do a little reminder in case it's like for multiple choice or stuff, but since it is based on this velocity, that means this is a vector quantity in these problems. So one of the most common things is to have something go this way and like hit a wall and then bounce off of it. That's almost like the perfect guaranteed little test question. Just make sure your velocity initial, and like in this case, would be a positive velocity, and your velocity final would be a negative velocity after it bounces off the wall. But anyway, and that kind of sets you up for what we're looking at next. This whole conservation of momentum thing, we're kind of looking at the fact about conservation of forces, and that's really where this goes back to. It's really all going back to Newton's third law is really where we're getting to here. Equal and opposite reaction forces. Because if you remember, one of the equations we picked up in Unit 6.1 was the impulse equation. Impulse is F delta T, and impulse is equal to mv final minus mv initial. It's just equal to a change in momentum. That's all that is. So, I mean, we could also say that is equal to delta rho. It's equal to a change in momentum is all this. Still good types of test questions right here. Anyway, so it should go to say that if two objects possibly ran into each other. So in other words, what happens if we had two balls? Why is it everything in physics involves balls? Oh, sorry, not meaning to get into a weird tangent there. But anyway, tangent. Secant. Oh, sorry, geek moment. Anyway, what happens if we've got two objects like this thrown at each other? We've got, say, this object M1, this object M2. This object has a velocity initial, which would be positive. This object, let's call it V2 initial, it would have, let's say it's got a negative velocity since it's moving towards the left, and we would need to call this velocity 1 initial. We need to keep those two separate. So what happens if you had two objects? Well, I want to see if this makes sense. Whatever force that this object hits the second one with, this object would be hitting with an equal force in an opposite direction. So see if this makes sense. The impulse of the first object would be equal to the negative, the opposite, equal and opposite reaction force, and equal and opposite reaction impulse from the second object. So based on this, I want you to look at something. This is where we derive an important equation from. That means that M1 V1 final minus M1 V1 initial would be equal to the negative of, so that would be negative M2 V2 final minus M2 V2 initial. I'll admit, what I hate the most about this chapter is all the twos and twos and ones and ones. And heck, for that matter, at some point you could work a problem with three objects all running into each other here. But anyway, we can take this equation, distribute here, rearrange everything. This equation, this is how we generally write it. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And this is actually our true conservation of energy equation right here. We use this equation for a lot. If you have two things hit each other and bounce off each other, if you have something that explodes like a gun going around shooting a bullet, and that's actually the first problems we're going to work are what I call explosion type problems. But we can work it all off of this. So let's go ahead and get started using this equation. I'll admit, for the purpose of physics team, I'm pretty lazy. We just go mv plus mv equals mv plus mv. We actually get very lazy doing that sometimes, but for the sake of these videos, we'll try and do it right. It's just everybody on the physics team knows that all your momentums must equal each other. It's not created or destroyed in these things. So let's go ahead and let's look at this equation in a little bit more depth here. A very common type of problem is this. A very common, I'll whack the camera a little bit. A very common problem is what I call an explosion. And that's where, say for example, that you've got a gun. Here's the gun. Maybe an old Western 6-shooter. Bing! And there's the bullet inside the gun. Let's put a little tip on the bullet. But anyway, wow, I can tell I'm not a kid anymore. I can't draw guns very well. Oh, look at this. Oh, she's a mighty beast of a weapon. Here's a simple little question here. What's the initial velocity of that bullet? Well, that bullet is just sitting there. It's not going anywhere. So let's call the gun M1, and let's say that bullet in there is M2. So my question would be, what is V1 initial? Well, the gun is just sitting here, just doing nothing. So that means its velocity is 0. And then we look at this object over here, M2 V2 initial, V2 initial, the bullet is just sitting there. Until you pull the trigger, nothing's going to happen. So that's 0. So I want you to look at something. So in an explosion, like when this bullet goes boom, think about what's going to happen. The bullet's going to get shot this way, and then it's going to apply force back against the gun, pushing the gun in the opposite direction. And if you've ever shot a gun, you know that kick we're talking about from shooting something. What does that mean in terms of this equation, though? Well, it means V1 initial is 0, so that's 0. M2 V2 initial is 0, so that's 0. And that's basically saying that in the event of an explosion, all your initial momentums are 0. So in an explosion, it's just M1 V1 final plus M2 V2 final. That's all that remains in the case of an explosion. And the one problem of this video is going to be an explosion. Some crazy kid has taken a batting machine and put it on the ice. Can you believe that? What some kids will do. So they've got a batting machine, they put it on ice, it's going to shoot a baseball, and the baseball, I don't know if you can read it, but the baseball is M1, and it's going to get shot that way. The machine is my M2, and it's going to recoil across the ice. So we've got this perfect explosion. So this problem, and this is example D on my homework, this problem, let's take a look at what we've got here. It says that M1, let's see, the baseball is 0.15 kg, if we can read that on my screen. I don't know that you can. And the machine is 50 kilograms. And the baseball has a speed of 36 meters per second. And so the question wants to know, what is the speed of the machine going backwards? Well, there's our equation. The initial momentum is all 0, so it's just 0 equals M1 V1 final plus M2 V2 final. So all we've got to do is 0 is equal to M1, the baseball was M1, so it becomes 0.15, times, I'm actually going to write units in. I know it's crazy, but I'm going to do it. Times 36 meters per second plus M2, which is 50 kilograms, times V2 final. And that's what we're looking for, is V2 final. So we end up with 0.15 times 36. So that's 0 equals 5.4 plus 50 V2F. So why did I leave these units up here? I want you to look at this. What's going to happen? The kilograms are going to cancel and leave you with nothing but a meter per second, which is what velocity should be. And so we're going to end up with negative 5.4 equals, and if you don't like me going through doing this algebra, that's your problem. It's my video. I'll do what I want. So move your 5.4 to the other side, and now divide negative 5.4 by 50. And the reason I wanted to show this, negative 5.4 divided by 50, I wanted to show you that this answer comes out to negative 0.108 meters per second. So there is my final answer. I just want to emphasize that negative, though, because this machine, when the ball is shot with a positive velocity, it should make sense that the machine ends up with a negative velocity in its recoil. So that's why I wanted to stress that importance on there. A very common thing in test questions would be to have answer A as positive 0.108, and then question D might be negative 0.108, and then B and C would be some kind of distractor numbers in there. Maybe 5.4 in case somebody forgot to finish the problem. That would be something that's usually done. But anyway, this gives you a good idea for an explosion. So in an explosion, it still starts with a MV plus MV equals MV plus MV. If you like to be a crazy person, you can go through and write your M1 V1 initial plus M2 V2 initial, M1 V1 final, and then M2 V2 final. But anyway, the moral of the story is this, though. In the explosions, shooting a gun, an astronaut in space throwing a wrench through the air or something, assuming that they're moving relatively still to their frame of reference, we can go ahead, mark all this out, and just write 0 equals. And anyway, that's again what makes what I call the explosion. Anyway, you've got a few problems you can do at this time. And next problems we're going to do, what happens if somebody throws something and they stick together? So next time we meet, hit and stick problems in elastic collisions. Anyway, thank you for watching, and please donate to turdferg.com. That was just a joke. I'm really doing this all for free. Thank y'all, and bye.